Okay, let's talk about computing the derivative of a function at a particular location using the definition of a derivative. So you need to start out um, with what the definition of a derivative actually is. So we have it here in the box. It says the derivative of f at x is given by f prime. Now, you can't hardly see it, but that does say f prime. So we have f prime of x. So that's how you would read that. And we have it written with the limit of f of x plus h minus f of x all over h as h goes to 0. Now, that's just one of the ways of writing that. There is a different way. Lots of times you will see upgraded versions of that where it means the exact same thing, and they will have the limit as the change in x approaches 0. And let's see here, they will have over here f of x plus the change in x minus f of x, if I can get it written over there, all over the change in x. So the h and the change in x are synonymous. So don't let that throw you off if you see it either way. Just know that this delta x is one entity. So if you ever had to square it or something like that, you would just write it that way. But it does not end up being delta squared and x squared. This is it. It's one little entity. Okay, but the big idea for us is derivative is actually slope. This right here, the difference quotient that is used here in the definition, that is derived from the slope formula. So it transpires that derivative is slope, and so we're going to use it in that way. So let's just kind of start with some basic problems and build up. Here's what I was telling you about a different way of denoting it down here, the limit. It could be, let's see here, well, here we go, my bad, it's right here, with your delta x going to 0. So there's just different ways of writing it. Doesn't necessarily mean they're different, just, again, derivative is slope. So we want to find the slope of a graph, f of x, at the point 2, 1. Well, first of all, please be considerate of how you write things down. Form is very, very important. So we need to start with f prime of x, which is saying, hey, this is my derivative. That's what you're telling people. I'm taking the derivative of f. Now, if you're going to do the derivative, you're going to use what's in the definition. So the limit as h goes to 0, and we can just actually write this down for right now so we know what we're doing. We're going to use the difference quotient. So at this point, I can come in here and I can substitute. And the way I've shown y'all to do this is just do them separately. You're going to do the x plus h here in this first section, and you're going to do f of x back here in the back. So when you do f of x, remember it's just the function as it is, 2x minus 3. Now whenever you do this part up here where you're evaluating it, x plus h, you're going to take your function, and wherever there's an x, open it up, and then you're going to go in there and you're going to put x plus h. And once you got it all situated, then you're just going to use algebra to reduce things. So that means we're going to come in here, we're going to distribute our 2x plus 2h minus 3, and then we have to distribute this negative. All those signs change. Now what I have told y'all is that any of these elements that come from the back term, they should cancel out. If they do not cancel out, then you have an error. So they do need to find a mate, and they do. And so let's get a little room here. This thing says the limit as h goes to 0 of 2h over h. Well, quite honestly, that simplifies. And you just have 2, and we haven't even done the limit yet. So then, if you evaluate this limit, there's not even an h. There's no substitution needed, anything. The rule for evaluating the limit of a constant, the rule says it's just that constant. Now notice what we've got. If we bring this down, we are saying that the derivative of the function is 2. It's not even like an equation or something. So we come over here and it said to find the derivative at 2, 1. Okay, now what you would end up doing if you wanted to evaluate the limit, you would get the x value. You really don't care anything about the y value. It's just the x value. Take your x value, plug it in. But guys, there's nowhere to plug in the x over here on the right. It's still 2. This is saying that since your derivative is a constant, it doesn't matter what value you put in for x, you're always and forever going to get a slope of 2, which should make sense because what kind of function did you start with? Oh, it's a linear function. Linear functions have the same slope no matter where you are. So that should make sense. Okay, let's get one that's a little bit more complicated. Let's go up to a trinomial that's representative of a quadratic. And so, you know, you're thinking about a quadratic, and the slope at different values of x is it's just gonna vary because you've got that nice curve. So this derivative is going to get a little bit more involved with the algebra, but it's the same stuff. Okay, so we got our limit. Don't forget to write it. Don't forget to denote your f prime of x. And then let's just go ahead and start plugging in. So we're going to say, oh, excuse me. Sometimes it's hard to write and talk at the same time. So let's see here. Wherever there's an x, we're going to open it up, put parentheses. That's the first part, minus, and then the second part is just copy down your function. Okay, and in the bottom we got h. So if we come in here and we put x plus h, now it's time to go with algebra. So if you're going to use algebraic means to break this down, we need to square, double square, square the first, twice the product, square the last, distribute your -3. Please be careful with your signs. And again, distribute the negative, which is always going to happen back here. And again, you have your self-check, which is every term in the back part should cancel. There should be an x squared, there should be a -3x, there should be a +5. Okay, with the terms that remain, everyone should have an x. And they do. So quite honestly, we could skip a step here, which would be lovely, and just go ahead and simplify the h's out. So if every term reduced by h, we have 2x plus h minus 3. Now you can evaluate your limit. If you evaluate your limit, put h in as 0, this term goes away and you just have 2x minus 3. Now that is the derivative of your function in general form. But this thing is saying, hey, what's going on at the point 2, 4? Well, you're only needing the x part. The x part is 2. So come in here, plug in your 2. Let's see here. And that's going to give me 4 minus 3 is 1. So my derivative, my slope, when x is 2, happens to be 1. That's what that means. All right, let's try a couple of other functions that are a little strange. I think we're good with the quadratics. These just feel a little weird. Going to work the exact same way. So your derivative is going to be the limit as h goes to 0. And once again, we're going to set it up where you've got your function, and wherever x is, you're putting x plus h. So that's the first set. And then the second set is that right there. Now, if you recognize this, that is that lovely little situation, so we really didn't even need to box it off. So if that's just too much going on for you, you do it like this. X plus h plus 2, because there's no need for the parentheses, nothing to distribute. No need for the brackets over here. We did this earlier when we were talking about limits, where if you have something with radicals in it like this, and there's no way to evaluate your limit by substitution. If you do, you get a 0 in the denominator, and it's undefined. But we really need to be able to evaluate this limit. So what we're going to do is we're going to rationalize the numerator. So think of this as a binomial. You got the square root minus the square root. Well, you need to do the conjugate. You need to do the same square roots, and pardon the wiggle in my board, but do the opposite sign. And if you will stack that up, where it is the same thing on top of itself. So this huge fraction that I just added in white, that fraction is actually synonymous with 1. So I'm not changing the value of anything, but I'm going to definitely change what it looks like. So I need to multiply these two fractions. Now the beautiful thing about the numerator is your design with conjugates is you're going to get the first terms multiplied together. When you do that, your radicals just go away and you just get x plus h plus 2. Now, think about the middle terms. If you had this first one times the last one, you get the positive version of that combo. If you do this last one with this first one, you get the negative combination. So they cancel out. That was the whole point of using the conjugates anyway. So the only thing that we really have to take care of next is the back terms. We have to get a minus because a negative times positive is minus. Block it off. This is going to be the square root of x plus 2 times the square root of x plus 2. It's just plain old x plus 2. The radical is removed. But please, please preface it with a negative, and you have to wrap up that quantity in parentheses so you can distribute. Now, I would highly advise that on the bottom, you just write them down side by side. Please do not worry about multiplying them out. If you do, you're just creating a headache for yourself for no particular reason. I'm going to write down this ordered pair so I can have it for later. All right, let's bump this up. We should be able to clean this without too much trouble. So I've got x plus h plus 2 minus x minus 2. And again, these from the back should be able to reduce. And as much as you might want to leave off this denominator, your form is imperative. Write everything. So the 2's cancel, the x's cancel, and I'm just left with an h in top. Now, depending on how comfortable you are, determines how many steps you skip. But it never hurts to show plenty of information. There's nothing wrong with the good old P formula. You don't want people to wonder that you don't know what you're doing, that you borrowed your information from someone else. If you reduce your h's, because that is legitimate because you have h times this whole group. So those can simplify and you just get 1. Now remember there's 1 in top now. We're going to do the limit as h goes to 0. And again, you can simplify this, make it shorter. So if now I evaluate my limit, so if the h part goes to 0, what I'm going to end up with is the square root of x plus 2 plus the square root of x plus 2, and that is, there we go, 1 over 2 square roots of x plus 2. And that's just my derivative. Now, my problem said evaluate it and see what my slope is at the point 2, 2. Well, I need to come over here and I need to plug in a 2 because that's my x value. So come over here in your derivative, plug in a 2. So I'm just going to go horizontally with this so I can quit scrolling down. So that's going to be 1 over 2 times the square root of 4, which is 1 over 2 times 2, which is 1/4. And that would be our derivative at that point. Now, in a separate video, we're going to look at rational equations and how they break down.